Assalamualaikum warahmatullahi wabarakatuh and a very good day. My name is Muhammad Nakib Muhammad Iqbal with ID number of 25534, a final year student of Petroleum Geoscience course in University Technology Petronas UTP. So for today's presentation is all about my extended assignment in Seismic Wave and Imaging course QBB 4123 lectured by Dr. Abdul Halim Abdul. Based on the question of extended assignment, I have been tasked to lead a seismic imaging team to pitch the new innovative seismic migration technique in solving the incoherency of the seismic reflection in Figure 1A and Figure 1B. I have been required to record a maximum 10 minutes duration of a video presentation on the suggested seismic imaging method for the PM311 region. Incoherency is the term that used in seismic data where it shows inconsistent of the seismic signal. In this slide, Figure 1A is on the left and Figure 1B is on the right is marked by the red circle where it shows the incoherency features in the seismic data image. In comparison of Figure 1B, it shows much more clearer in terms of signal and the signal is more continuous compared to Figure 1B where the signal is much more distorted. The incoherency that we showed in the slide just now is due to the shallow gas anomalies. This is because of the presence of the layered gas field sediments. The layered gas field sediments will produce strong multi-cutting and will lead to amplitude and frequency loss. This will also be reflected as a fault structure and a poor event continuity. The layered gas field sediment also will disrupt the propagation of seismic wave from sources to receivers. In other words, it will give complex propagation. This event or the presence of layered gas field sediments will also induce other seismic problems such as scattering, dispersion, and internal multiples. We could see the significant deterioration of seismic image and the strong lateral variation of seismic velocities, where this will lead into a problem during the processing, interpretation, as well as the imaging. Based on the problem that we stated just now, I would propose three major methods to compensate this problem, which are Q migration, illumination factor analysis, and common focal point. The first proposed seismic migration method is by using the Q migration. This method is implemented from Kirchhoff, beam and reverse time migration RTM. It will be correcting the seismic amplitude and the distorted phase wavelength. It used estimated absorption model for frequency-dependent Q tomography to compensate for Q effects relative to the background. It goes beyond simplistic surface consistent assumptions to compensate for transmission effect anywhere in the overburden. This Q migration method will give more accurate prediction of reservoir properties as well as easier identification and interpretation of the pull factors. As you can see on the right side, the first image is before applying the Q migration, while the second image is after applying the Q migration, where we could see by marking at the red circle, the seismic signal is much more clearer and continuous compared to seismic image before applying the Q migration. The second proposed migration method is illumination factor analysis. This method is actually a combination of ray tracing method and the focal beam method to create a new function of analysis. Ray tracing method is relying on the number of ray hits on the reflector, which this method cannot incorporate through amplitude information. Focal beam method, on the other hand, is a method that performs quick illumination analysis after the production of velocity model of the subsurface. This method only provides information as specific target point, and the illumination analysis at other areas are unknown. So by combining the two methods, ray tracing and the focal beam method, the illumination factor analysis could give a better accuracy on the location of gas cloud within the subsurface, as well as better indication of illumination distribution of the gas cloud. Illumination factor analysis starts by the production of comprehensive velocity model from field velocity information. Then, from reflector depth of interest, wave is sent to the surface level towards source and receiver. The wave is convolved with source and receiver before propagated back to the target reflector. The ray tracing is done after focal beam had finished by the same acquisition center. Fans of rays are propagated through layers and anomalies to target depth before reflected back to the surface. Lastly, the mathematical manipulation for calculation of illumination factor as basis for new illumination analysis. In short, you can see on the right side is the workflow for this illumination factor analysis, where this method could help compensating the incoherency features that we could see in the seismic data image just now. The third proposed imaging method is by using the common focal point, or in short CFP. It uses a focusing operator, one with travel time function between one point in the subsurface and all acquisition points at the surface, without estimating the corresponding velocity model. It uses spline genetic algorithm parameterization to estimate the focusing operators. This imaging method will give improvement in lateral reflective quality and restore the amplitude in the subsurface. It also gives a better amplitude below surface complexity, where in this case the gas cloud. Then, if the amplitude has been restored, more energy can be retrieved and be imaged and will lead into a better interpretation. This common focal point method starts by identifying horizon, and then it will use as apex time for the initial focusing operators for each boundary. Then, by applying Fermat principle, it will combining two one-way travel time functions for each source visible. QC one-way focusing operators and the reflection events are expected to be at zero offset. Next, interpolation algorithm to obtain the focusing operators for each vertical apex time and each lateral focal point position. Lastly, producing velocity depth model by tomographic inversion algorithm with focusing operator times as an input. As you can see on the right side, this is the comparison by using the Kirchhoff time migration and CFP one-way time migration, where the latter give much more better seismic signal compared to the Kirchhoff time migration. In short, to compensate the incoherency that been seen in the seismic data image, I would propose Q migration method, illumination factor analysis, as well as common focal point in this project.